There we go. So the topic today will be beamforming. We are going to be doing a few introductory demonstrations about beamforming and also interferometry. And as we will see, beamforming and interferometry are in a certain way two sides of the same coin, so they are tightly related. And the reason for doing this tutorial today is next week we will be visiting the Allen Telescope Array. And as you will see, there is an array of 42 antennas, not all of them operational. So with this tutorial today, you will be able to understand better how this is supposed to work. And when you use the beamformer, you will know what is the signal processing that is happening behind the scenes in the telescope software. So the flow graphs are in the beamforming folder. These are already uploaded, and we will be working first with this beamforming demo and then with the beamformer array demo. So here am I in GNU Radio Companion. I'm going to be doing this one from scratch, but copying and pasting a few sections from the beamforming demo finished flow graph to save some time. So let me just here beamforming demo 2. The sample rate, I need 1 million samples per second. That gives me 1 megahertz of bandwidth. And this is a simulation, so we could make this anything we wanted. 1 megahertz is okay for low CPU usage, but you could do whatever. And then let me save this as beamforming demo 2. So the first thing, I'm going to copy and paste all of this because it has already appeared on one of the first tutorials. So what is this? This is the generation of a wideband signal. So it's a noise signal which is occupying a bandwidth of 1 kilohertz, and we can change that with a GUI parameter. And it has a center frequency at 50 kilohertz. We can also change that, and we can change the SNR. So in one of the first tutorials, we saw how to generate wideband and narrowband signals with different SNRs and how to measure the SNR on the spectrum. I have just reused part of that flow graph. So we have the noise source, the resampling to set the bandwidth, and then we have this multiply by the signal source to shift it in frequency, and the throttle block because this is a simulation and we want to run it at real time. And the thing this is supposed to represent is some kind of astronomical signal. I'm just using a wideband signal, but with finite bandwidth, so it doesn't occupy all the 1 megahertz bandwidth we're using because of simplicity and also because it's easy to see the signal and tell it apart from the noise floor in the spectrum plot. Real world astronomical signals, they might be like this if they are spectral lines with some Doppler spread. But most of the astronomical signals are wideband. They occupy essentially all the radio frequency spectrum, so hundreds of megahertz and even gigahertz, and they would be wider than our bandwidth here. So that would look like uniform noise source across the spectrum. And of course, it's less easy to see what's the signal, what's the noise, if both have the same shape. So that's the reason I'm doing this today. But what I'm doing carries over to any kind of signal you want to put in here. It can be also a techno signature type, an artificial signal, a satellite signal, whatever. So we have our astronomical signal, and I'm not sure if I've used before these virtual sync and virtual source. These are just a way of connecting parts of the flow graph without running one of these connection lines like so. Because if you have many connection lines, then the flow graph might become too crowded or too tangled. And so what you can do is to set some stream ID here, which is just a name. And then you can have one or multiple virtual sources with the matching astro signal. So this needs to match. on the sink and the source, and you can have as many sources as you want rather than running a direct connection. So it's a way to keep things nice and tidy. So what I'm going to do here is to simulate first one antenna. So I'm going to add a node here. This will come in handy. Antenna 1. There's this node block which can be used to add just a node. But in every block, you also have this comment which will appear below the block. So if you want to document things, you can also use these comments. So if we have an antenna receiving this astronomical signal, the antenna, or actually the electronics in the antenna and the receiver, will generate some noise. I'm going to mimic this noise with a Gaussian noise source. And then I'm going to use a seed of 1 because I want each of my noise sources in the flow graph to have a different seed because they are really independent different sources of noise. So what did I do? Yeah, okay. So in this way, the noise source which corresponds to the signal has a different seed from the receiver electronics on antenna 1. And then what happens in antenna 1 is that whatever signal or signals come from the sky get added to the receiver noise floor. And then we can use a GUI frequency sync. For the time being, just one input to show how this looks like. So this will be not very surprising. Okay, I have the averaging, so that's the reason this is coming down. Maybe I can set medium average. So we have 0 dBs SNR. That means that the power of the signal of interest, which is this part of the spectrum, is the same as the noise. So when we measure here both the signal and the noise power, we get a 3 dB. 3 dB is a factor of 2 raise in the total noise compared to the noise floor, which only has the receiver noise. So this is something we already did. Now what I want to add is a second antenna. So the second antenna will have basically the same thing, but the noise source is going to be different. So these two Gaussian noises are going to be independent, randomly independent or independent random variables. And we will use that to our advantage in a moment. But for now, let's just check and see that in antenna 1 and antenna 2, we get pretty much the same signal. We can see that the noise is different. So the two noise sources have the same power, but since they are uncorrelated, they are different realizations. So every time we measure the spectrum, we get some random wavy thing, which is different in the red and blue channels. But so far, these two are the same. And now the main idea of beamforming is we have these two antennas. So they have some collecting area. You can imagine some dishes collecting the radio frequency energy, which is arriving. And essentially, depending on the size of the dish, you collect more or less amount of radio frequency power. And of course, having a larger dish is better. But the question is, if we have two dishes, then each of the dishes is collecting some amount of power. If we want to add those powers, how can we do that? If there's a way to do it, we should be able to collect twice as much signal power, provided the dishes are the same size. Because by adding the areas, the collecting areas of the two dishes, we have twice the area. So in this simple example, since we have the astronomical signal in both of them, and it's exactly the same astronomical signal, what I'm going to do is to add the two signals together. In a moment, we will see why this is not a very realistic scenario. So I'm just doing this as a warm-up. But if I add these signals together, what should we expect? So we have a combination of two sources. One is the astronomical signal, which is common in both of them. The other is this Gaussian noise source, which is different and independent. What should we expect about the addition of these two antennas? So on the astronomical signal, since it's exactly the same here and here, when I add two things which are exactly the same, that's just multiplying by 2. So in here we have the astronomical signal multiplied by 2. And by multiplied by 2, I mean multiplied by 2 in amplitude. These are complex numbers, so if I add 2 copies of the same number together, I just increase the amplitude by 2. And something we need to remember is that the power is the square of the amplitude. So if here I have twice as much amplitude, then I should have 4 times as much power. If we think about this in physical terms, it doesn't make so much sense because if we have 2 antennas, then we expect that the power adds up and we end up with 2 times as much power rather than 4 times as much power. But the thing is, this is just because of normalization. Here I'm adding the 2 signals. I could also take the average, or I could also add and divide by any number I want, or multiply by any number I want, because this is the digital domain. So there's really no physical units here. So it's fine to say that the power is 4 times as large as here, even though we know that physically we would get 2 times as much power. That basically means that we have a factor of square root in the normalization here to relate the arbitrary units of power we have in the digital processing to real physical world units of power. So this is what happens with the signal. Basically, we get factor 2 on the amplitude, factor 4 on the power. What happens on the noise? That is slightly more difficult to discuss because we need to remember something from statistics. And that something is that when we have 2 uncorrelated random variables, if we want to know the variance of the sum, it's the sum of the variances. So that's just because of the signals are uncorrelated. If they are correlated, you can get something else. So we have here these 2 uncorrelated signals, and something else we need to know is that the variance of this random variable is the same as its power, because the variance is the average of the amplitude squared, so to speak. So it is the RMS power. So that means that if we add these 2 signals, then the power adds. So we have power 1 here that is set by the amplitude, power 1. So we end up with twice as much noise power. So the signal power is 4 times, the noise power is 2 times. And then what happens is really we only care about signal to noise ratio because we could multiply this by 10 or by any number we want. And of course, both the signal and noise would increase in power by the same amount. But by doing this addition, we are increasing the signal power by 4, increasing the noise power by 2. So the signal to noise ratio gets increased by 4 divided by 2, which is 2. And that's one way to arrive at the physical conclusion, which is if we add up the 2 collecting areas for the 2 antennas, as they are the same size, and that's represented by them having the same amplitude here, we should get twice as much signal to noise ratio. So let's now run this and check if that is true, more or less, because it's not so easy to measure signal to noise ratio with this somewhat weak signal. Maybe I will make it somewhat stronger for the measurement, because if we want to measure precisely, then here the signal to noise ratio, as I mentioned, is 0, but we see a 3 dB increase because we are adding signal and noise. So we need to be careful in doing that calculation. And to do it better, what I can do is just make my signal much stronger for the time being. And then what happens is Now I can ignore the noise power because the signal is 100 times, so 20 dB is 100 times stronger than the noise. And what I can see here is the signal is at minus 24.5 maybe in each of the antennas, but in the beamforming is at minus 18.5. So the difference between minus 18.5 and minus 24.5 is 6 dBs as we had calculated. And then what happens with the noise floor? So the noise floor is at minus 44.5 maybe. And in the beamformer is at minus 41.5. So again, the difference, minus 41.5 and minus 44.5. So that's 3 dBs. We see that the noise has increased by 3 dBs. The signal has increased by 6 dBs. So we get a 6 dB increase in signal to noise ratio. And in fact, that's quite apparent now if you look at the difference between the signal and the noise. This one is 3 dBs stronger than with each individual antenna. So that's a way to add multiple antennas, and we could have a signal which is so weak that it's not possible to detect in one single antenna, but it's possible to detect in the combination of 2 antennas or 10 antennas or however many. So maybe, for example, if I try minus 4 dBs to try and have a weaker signal, or maybe even minus 6 dBs, you can see that the signal in each individual antenna is now not so easy to tell apart from the noise floor, but in the beamforming combination, we can still make out the presence of the signal since we have this 3 dB advantage. So it would be minus 3 dB on the green line. Okay, any questions at this point? So what is not so realistic about this scenario? The thing that is not realistic is that I'm feeding exactly the same signal to the 2 antennas. And in real life, that doesn't happen because the antennas are not exactly in the same place. So you can think about 2 antennas on the ground. They will be some distance apart. And what happens is that the signal is traveling from the astronomical source, wherever it is. And to arrive to the antennas, in general, it will not be the same distance. It will not travel the same length because the astronomical source will be more near to one antenna than the other one. For example, you can think of 2 antennas. One of them is on the east side, the other is on the west side. So what I'm thinking of is just draw a line from east to west and put 2 antennas in there. You have an east antenna and a west antenna. And then if you have your astronomical source on the eastern part of the sky, the east antenna is nearer to the astronomical source than the west antenna. So the signal coming in from the astronomical source arrives earlier to the east antenna than to the west antenna. So that's something that happens. We get different delays, and the delays not only affect the signal delay. Here we have this delay block, which would accomplish is to delay the signal by a fixed amount of samples. But they also affect the phase of the signal because the signal is a radio frequency signal, so it has a radio frequency carrier wave. And if you delay all the signal, including the radio frequency carrier, the radio frequency carrier is a sinusoid. But if you delay a sinusoid, it's like changing the phase of the sinusoid. So what happens is the signals arrive with different phase. And also what else happens? The thing that happens is that this scenario is constantly changing with time because Earth rotates and the position or the apparent position of our astronomical source on the sky will move. So the source will rise in the east and set in the west, coming back to the situation of one east antenna and one west antenna. initially, when the source is rising, the east antenna is closer to the source, but then the source goes through culmination, and the distance to both antennas is the same, and then the source continues moving west, and at that point the distance is closer to the west antenna. So that means that this difference of distance, which is the thing we want to care about, because we want to compensate for the fact that the signal has traveled for different lengths or for different times before adding together. So we only care about this difference of distance, not the absolute distance. This difference of distances is constantly changing. That means the phase is constantly changing, and a change in phase versus time, as we saw in the previous tutorial, is the same as Doppler. So what happens is that the Doppler frequency on one antenna is not exactly the same as on the other antenna. The difference is very small. It's usually a few hertz, depending on the frequency, but it's already enough to be something we can handle. In fact, we will see what happens if we do not handle it. So what we want to do is to keep one of our antennas as the reference antenna, let's say, and this is just for the purpose of the simulation. Usually in beamforming and in interferometry, there is the concept of a reference antenna for calibration, but here I'm just using it for the simulation. So what I'm going to do is, since I only care about the difference in Doppler, the difference in delay, the difference in phase between the two antennas, I'm going to apply that difference to the antenna 2 and leave antenna 1 untouched. And that's one way to do it. Of course, I could apply some changes here, some changes there, and I would only care about the difference in frequencies, delays, and so on. So to do that, I'm going to use a new block. Let me copy and paste this too. I think I haven't used this channel model block. The channel model block is used to simulate a more complicated propagation channel than just adding noise. So in a sense, it's a replacement for this noise source and addition, and it has extra options. So you are supposed to run your signal through it. And then the options you can set is the noise voltage. That's the same as the noise amplitude on the noise source. So internally, this block is composed by a few blocks, and one of them is a noise source, and the voltage you set here is the amplitude of the noise source. Then you can have a frequency offset, and the units of the frequency offset, I think that's in the documentation, are cycles per sample. So they are related to the sample rate. For example, if I set this to 0.1, this would be 10% of the sample rate. And in general, we will see how we can compute this value. Then epsilon means the change in delay versus time. And this is in parts per one. What does parts per one mean? Usually we add here a very small number. So for example, 1,000th. And this means that for every second that we advance in time, the difference in delay will increase by 1,000th of a second. So usually delay rates are measured in parts per million. 1 part per million is 10 to the power minus 6. And that means that every second, the delay increases by 1 microsecond, which is 300 meters. So as you can realize, that will not be the case for just this situation. For an astronomical source, which is on the sky and the antennas rotating, just from the rotation of Earth, we do not expect a change in 300 meters unless the separation between the antennas, which is known as the baseline, is really, really large. So usually we will have less than 1 part per million of epsilon. The tabs here are used if we want to simulate multipath. So multipath means when the signal bounces of several objects in its way to the receiver, and then it arrives. So one part of the signal arrives to the receiver at some point. Another part of the signal has gone through a different path, bouncing of another object, and then arrives later to the receiver, and then another path, and so on. That doesn't happen in radio astronomy because there is not much between our antennas and the astronomical source. Of course, there is the interstellar medium and there is plasma, so there are some interesting effects in there. But this multipath is really intended for terrestrial propagation communication. So you can think of a cell phone tower and the cell phone you might have in your pocket. The signal between them is bouncing off many buildings and the walls and ceiling of the room you're in. So that's the reason we have these tabs, and we can mostly ignore it for our purposes. And the seed is the seed of the noise voltage. So in here I have, I'm just adding noise and then keeping the parameters by default to not to change the frequency, not to change the delay, not to change anything else. In the antenna 2, let's see, I also have some entries to be able to change these values from the GUI. And the values we are going to be changing are the phase difference between the antennas in degrees, the frequency difference between the antennas in hertz. So this would be the Doppler difference, the delay rate difference between the antennas in parts per million, and finally the delay difference in samples, which we cannot do with this channel model. So we will add an external delay block. So what do we have in here? As I mentioned, the frequency offset is in units relative to the sample rate. So in cycles per sample, if I have this in hertz and this in hertz or samples per second, I can divide them and I get the appropriate units here. And then my delay rate difference is in parts per million. So to arrive at the epsilon, 1 part per million is 10 to the power minus 6. So that's the calculation. And then I'm actually using the tabs here, so I should explain what does it mean to set the tabs to something. This can be used to multiply the signal by any complex number we want. So in here, we are multiplying the signal by 1, so that means we are leaving the signal untouched. And in here, we are multiplying the signal by e to the 1j, so this is an imaginary unit, and the phase in radians. So this is a phase shift. This achieves the intended phase difference between the antennas. And I have C2 because I want a different noise source. So what else? Delay blocks. We want some delay blocks, this one. So what I also want to do is to add an additional delay. So this is the delay difference. And I'm not sure if this block supports a negative delay. In the past, it didn't support a negative delay. I think that now you can use a negative delay with some limitations, but anyhow, we can test it. So now we have all these parameters that we can change on the GUI, and they represent the fact that the signal that is arriving to the two receivers is not the same because it has traveled different distances, basically. And let's try to see what happens if we still insist in adding these two signals together, even though we know that we need to apply some corrections. So what happens is maybe I'm going to make the signal to noise ratio larger, and I don't need that much averaging. So at the moment, I have all of these extra variables set to 0. That means that the signals are still the same, arriving to the two receivers. But we can now check and see what happens if we play with these values. So if we start changing the phase 30 degrees, maybe we have seen this green drop a little bit. Maybe not. Yeah, in fact, probably you can see it dropping 90. So now it's clear that if I increase the phase difference, the two signals are not adding together to produce twice as much amplitude, but less. For example, if I add two signals which have a phase difference of 90 degrees, then the final amplitude I get is the square root of 2. So that means the signal to noise ratio increase would be 3 dBs here, but we also have 3 dBs on the noise. So basically at this point, we are not increasing the signal to noise ratio by beamforming. And if I continue, so if, for example, I make this 120, at this point, beamforming is counterproductive in the sense that the noise floor has increased, but the signal hasn't, because the signals are not in phase, so they are canceling each other. And if I continue, maybe I can make this 170. So 170 is almost 180, and 180 degrees is the opposite. So when I reach 180 degrees, we will see that the signals completely cancel out, and then we lose it completely. This might seem pointless, and in fact, to observe a signal which is a signal of interest, it is pointless. But now you can imagine that the signal here might be an interference, for example, and then if you add if you have common interference on two antennas, if you add the interference with 180 degrees of phase offset, then the two interferences cancel out. So this is called null forming. It's in a certain sense the opposite of beamforming. You can produce nulls in your antenna radiation pattern, and that means that when a signal is arriving from that direction, it will be completely canceled, and you can use that to cancel radio frequency interference. But anyhow, coming back to our discussion here, we have seen that we need to have the signals in phase. Otherwise, when we add them up in the beamforming combination, they cancel each other out, or at least they do not increase as much in amplitude as they should. What happens if I have a frequency difference? A frequency difference causes a change in phase difference versus time. So if, for example, I set 0.1 hertz, 0.1 hertz means one cycle every 10 seconds. So we will see that every 10 seconds, the signals are combining constructively, and then destructively, and then constructively again. So let's see that. Now they are constructively, now they combine destructively. And yeah, maybe that was too fast because I have the average. So let's maybe turn the average down and make this 60 or something. So hopefully it will be easier to see. Yeah, now this is decreasing. It actually happens very rapidly because the zero crossing is quite rapid. But you can see that the signal power is fluctuating up and down. The very fast happens because of the dB scale. So in fact, this is called fringe rate, and it is how the first interferometers worked. What they did was they had one, two, or several antennas, and they added up the voltages from all of the antennas, and then depending on the Doppler, we would get some sinusoid on the power, and that sinusoid could be detected, and from the phase of the sinusoid, something could be said about the position of the signal on the sky. So that's how earlier interferometers worked, by detecting this fluctuation when we do not correct for the Doppler difference. But nowadays, we basically correct for all of these, since we know where our source is located, and We have the digital signal processing power to correct for all of this. So it looks more like what I'm showing here. Let's reset this one. And then what else can we show? So for the delay difference, I'm going to set medium averaging, and I'm going to make my signal much wider. So for example, maybe 350 kilohertz or even 600. And in a second, it will be apparent why I am using a different signal to demonstrate this. So first, I'm going to show what happens if I set a delay difference of one sample. We see that at some part of the spectrum, the signal is decreasing. At some other part of the spectrum, the signal is increasing. And maybe this will become more clear if I increase this number. So for example, 3 samples. I have a notch here. This is called a notch or a null. So at this frequency, we get destructive interference. At this frequency, we get constructive interference, destructive, constructive, etc., etc. And we get the same pattern with 3 notches in all the spectrum. We can only see 2 because we only have 600. If I said 950, we might be able to see the 3rd notch on the signal. So why this happens? This happens because a delay is the same thing as a phase change, but it depends on the frequency of the signal. So over all the spectrum here, we have different frequencies. And for 0, which is here in the middle, any delay is no change in phase, because a signal which is a constant voltage, a DC voltage, you can delay it as much as you want, it will not change in phase. But if we increase in frequency, then at some point we get a delay difference that is equal to 180 degrees for that particular frequency. And at that frequency, we will get cancellation. And then at some point, the phase difference is equal to 1 cycle. So 1 cycle is the same as no phase delay, because phase is modulo 1 cycle. So we get constructive interference, then 1.5 cycles, and then that's destructive interference, and so on. Why is this pattern not symmetric in the spectrum? That is because I have stopped the frequency difference, but there is some phase offset between the signals. In fact, I can demonstrate this starting again from scratch. So 900, 0, 60, and then 3 samples, and I haven't touched the frequency difference. So the destructive interference happens at symmetric points. If I set a phase difference of 30 degrees, you can see that on top of the delay caused by the, so on top of the phase caused by the delay difference, we add 30 degrees. So now the points at which there is destructive interference change. And if I set 50, they change. But what you see happens in general. If you see 3 nulls across your spectrum, that means delay difference is 3, and that's not special about 3. We can set 10, and then we get 10 nulls. I'm not going to count. So that's what a fixed delay that we do not correct for looks like. And a delay rate difference basically looks like a continuously changing delay over time. So if I set these to 1, you can see that there is some null appearing and moving through the spectrum, and then there are more and more. Maybe this is better if we do it slower. So you can see that this wavy thing is compressing because we are continuously increasing the delay. So we are introducing more nodes across the spectrum. So that's how a delay difference looks like. And the point of all of this was to demonstrate on the spectrum of the beamforming combination, if you just add up those two signals, how different effects will look like. Then what does a beamformer do? The beamformer does, so this is the simulation. All of these would be the real physical world. And then in here, we would have our receiver. And what we do is basically the opposite of these two, since we know where the astronomical source is located on the sky, where our antennas are located on the surface of Earth. We can compute even ahead of time all the parameters, the phase, the frequency, the delay, and correct for them. I'm not going to demonstrate that in GNU Radio because it would be slightly tricky to get this synchronized with some correction, and somewhat pointless because since this is a simulation, I can still skip this. So there's no point in adding a block which corrects for the effects of this block. And in fact, the correction block could be the channel model with this set to 0 so that it doesn't add any noise, and then the opposite parameters from the previous channel model. So yeah, if we do some changes to the signal and then we undo them, we arrive at the initial signal, and then we can add the two of them together. And that's how real world beamformer works. But you need to keep in mind that this is our receiver together with the corrections at the inputs here, which I'm not including. And all the rest is the real physical world, which I'm simulating here. Okay, questions at this point? Good. So there is something else which I haven't mentioned. I've mentioned that if we want to correct for this and this, we know the positions of the antennas, we know the location of the source on the sky, so we can compute all of these effects a priori. And that is only partially true because the antennas have some cables running to the receivers, and those cables have a certain length. Maybe we do not know the length of the cables exactly. Well, we could measure the length of the cables, but even so, we actually care about the time that the signal takes to propagate through those cables, and that's dependent on temperature. For example, if we really want to get precise, it matters the temperature of the cable because it changes the physical properties with temperature. And also the electronics themselves can add some delays, some electronic delays, and some phase offsets just because of how things work. And those can again be temperature dependent, frequency dependent. So there is actually no reasonable way or practical way in which we could know all of those parameters beforehand. So what we do is to measure them and calibrate the phases, calibrate the delays. And once we have calibrated once, then we use our model of where the source in the sky is, where our antennas are on ground, to continue changing these parameters. So the calibration is usually done only once or every few hours. It depends on how large your interferometer is and how rapidly over time these instrumental phases and delays tend to change. But for example, for the Allen telescope array, the calibrations are good for many hours, and usually you calibrate at the beginning of an observation and then you go and use the beamformer without doing any more calibrations. So how can we do these calibrations? The idea is to use a source on the sky, which is usually a quasar because they are broadband in frequency and also they are point sources. And point sources means that it is really the same signal arriving to both antennas except for these corrections, let's say, that I'm adding. Some sources on the sky are not point sources, they are extended. When you look at them, they have some angular size. And then what happens is that basically the signal arriving to each of your antennas is slightly different on top of all of these corrections, so they are not good sources for calibration. But point sources, so very distant quasars, of which we know the location of the sky very precisely, are great sources for calibration. And then when we have our source, let's pretend this is a quasar. What we want to do is to measure the phase and the delay difference between the two antennas. And once we know that, we can add the corrections here. And I'm using two antennas for the sake of the example. The same thing works with many antennas. You just do pairs of antennas together. So how can we measure the phase difference between these two signals and the delay difference? The idea is to use something which is called a correlation, and I'm going to copy all of these and explain, because this is quite similar to what we've been doing to plot spectrums with the fast Fourier transform. So the correlation is a mathematical way to find how similar two signals are, so to speak. It will compare two signals, and if the signals are similar, you will get a high correlation value. If the signals are completely independent, for example, our two independent random noises here, the correlation will tend to be 0 or a small number. So in a certain way, the correlation is measuring how similar two signals are, but the correlation is also a complex number. So it's not only measuring how similar they are, but also if there is some phase difference between the antennas or the signals, and the phase difference will appear as the phase of the correlation. And we do this over frequency. So not only we are looking at the phase difference at one single frequency, but at each frequency in the spectrum. And then what happens is we have seen delay is the same thing as a change in phase offset versus frequency. So if we get some phase offset versus frequency, then we can recognize that as a delay. So what I'm missing here, some integration time and some FFT size. So I'm going to do FFTs of size 256, integration time 0.1 seconds. That is good enough, and we'll make the plots update faster. And what we do is we do the FFT of each of the antennas, and then the key ingredient of the correlation is this multiply conjugate. So when you have two signals which are similar, the multiply conjugate will tend to give you the same complex number over time. And the phase of that complex number will indicate the phase offset between the signals. If the signals are completely independent, this output will be random and it will have random phase. So the next thing we do is we integrate. We are integrating complex numbers for our intended integration time. So we are generating one measurement every 0.1 seconds. And then what happens if the signals are correlated? This is more or less constant over time. So when we are integrating, we are adding constructively. If the signals were completely unrelated, this would be random. And when we integrate something random, things tend to average out and we get something close to 0. And finally, what I'm going to do is on one plot, I'm going to plot the phase. So the phase is the complex argument. And this goes from -pi to +pi. The repeat is the trick to have the plot update faster. And on another plot, what I'm going to do is to calculate the inverse FFT. So this is the inverse FFT. And do the complex to magnitude squared. So I'm showing the inverse FFT in power. And this is called lag domain, which means delay domain. and we will see how this looks like. It's better to understand it with an example. So let's make this somewhat stronger, or maybe not, because then I need to rescale my plot. So I guess this is okay. This is the phase. And in here, which is where my signal is present, I get a phase difference of 0. So this can be read as a phase difference of 0. In the rest of the spectrum, I get something completely random. And if I were to plot the amplitudes here, I would see that the amplitude here is large and the amplitude there is small, because this is noise, uncorrelated noise. But mainly I care about this phase. If I set, for example, 90 degrees of phase, then I basically get minus 90 degrees. And yeah, probably there is some sign convention that needs to be taken care of, but basically we can read the phase offset here from the plot. So 180, for example, it would appear on top and on bottom. Since there is a little bit of noise, it's somewhat confusing to read this, but maybe 200 is more clear. And for sure, if I set Doppler, we can see that the phase is changing versus time, and we can clearly see when it returns to 0, for example, and stop it by setting the frequency again to 0. How does the delay look like? Again, to demonstrate that in a more clear way, I'm going to make these much larger, such as, for example, 800, because if I set a delay of 1 sample, then we get the phase looks like this, and basically it goes from minus pi to plus pi once across the full spectrum. So this is called one phase wrap. It basically goes a full turn when you move across the spectrum, and that means 1 sample. If we have 2 samples, then 1 wrap, 2 wraps. We have 2 wraps, and if we have 5, well, we have 5. So we can directly read the delay from here. What is this lag domain power used for? So maybe counting here is not so easy. For example, if I have 25, it's somewhat cumbersome, not only for us humans, but also for numerical processing on the computer to count if this is 25 wrappings or 24 or 20 something. So we have these, I'm going to use the auto scale. So we have this, which is the inverse Fourier transform. And the inverse Fourier transform shows a peak at the appropriate delay, which would be minus 25 in this case. Again, a sign convention, but basically 256 minus 25 should be 231, if I'm not mistaken, which is the location where the peak is to be found. And we can see how this looks like if I go and change this smoothly with a delay rate difference. We can see that this is increasing now in the other direction. So now we can see the peak moving, and it's moving from 0 to 1 sample, 2 samples, etc., etc. So to calibrate the real telescope, we would do something like this. We would observe a quasar, which would be a wideband signal. It would occupy all the spectrum rather than only this 800 part. And we would look at the phase, and we would need the phase to be flat, basically. And if the phase is not flat, if it does wrappings like this, that means there is a delay, and we can measure the delay in this kind of plot and correct for it. If the phase is offset after correcting the delay, so for example, if I return this, zero, okay, close enough. So once we have corrected for the delay, if the phase is not at 0, so for example, here at 90 degrees, we know there is a phase offset between the antennas, and we also take note of that. And that is our calibration. The calibration is basically what is the delay difference and the phase difference between each antenna. And usually the delay difference does not depend so much on frequency, on the observing frequency, whether we are observing at 1 gigahertz or 8 gigahertz or whatever. But the phase difference depends a lot on frequency. So you need a different calibration for each of your observing frequencies. So what I'm going to use now is this beamformer array demo. And so far, I've only been focusing on one aspect of beamforming, which is we have multiple antennas. So when we beamform, we add the signals together and we basically improve our signal to noise ratio. And that is equivalent to adding the collecting surface area of all the antennas. But there is also a very important aspect of beamforming, which is whether we like it or not, because it might be beneficial in some cases and not beneficial in other cases. Something else happens with beamforming, and that is that the antenna beam pattern, the antenna radiation pattern changes and becomes more narrow. So the antenna radiation pattern tells us at in which part of the sky the antenna is sensitive to. And what you might already know is if we have a small dish, the small dish not only has low sensitivity because it has low collecting area, but it has a large beam width. So that means it's able to receive signals from a wide area of the sky. If we have a very large dish, then it has a large surface collecting area. That gives us much more signal to noise ratio, but only in a small area, which might be 0.1 degrees radius or even less. So that happens with one dish if you change the size of the dish, but it also happens with beamforming an array. And here I'm going to use an example of Steve Croft, which I like. And that is, you can think of an interferometer in the following way. You start with a very large single dish, which occupies the whole area in which your antennas are located. And the dish is very sensitive, and it has a very narrow beam width. And then what you do is you punch out holes on that dish. And of course, you're losing surface area, but you are not changing so much the antenna beam pattern. So it still has a very narrow beam width, because the beam width has more to do with the total size of the dish or the diameter of the dish, rather than whether all the surface area of the dish is filled in or not. And if you continue punching holes, then at some point only your array antennas remain. So you might have several dozen small antennas instead of the original very large dish. And surface area has decreased, but the beam size is still the same as with the large dish. So I want to show this effect here so that we get some more understanding about why that happens, how that happens, and what is beam forming actually, or beam steering. So how can we actually point the location on the sky where beamformer array is looking at? And for this, I'm going to simulate the most simple kind of beamforming array, which is called the linear array. And I'm going to use this picture from the internet as a reference. And it's called a linear array because all the antennas are placed on a straight line, and the separation between the antennas, for simplicity, is uniform. When we arrive at the ATA, we will see that the antennas are randomly scattered over field. So that's quite different from this. And there's actually a reason for randomly scattering antennas, but that's more complicated to simulate. So I'm going with this. Since the array is on a single line, then everything is on a plane, so you can draw nice diagrams and use plane geometry. In general, you would need to use 3D geometry. So what happens here is maybe the radio frequency signal is coming from this direction. And this is what I was explaining before. This antenna is nearer to the source than this antenna at the far end of the linear array. So what happens is that there is a time delay t between this antenna and this antenna, also the same time delay t between this antenna and the same delay between these two antennas. So this is what I was explaining. If we want to combine the signals to form this output signal, we need to delay this by 3t, this by 2t, this by t, and this doesn't need to be delayed. So the delays here account for the time advance, the fact that the radio frequency wave arrived 3t earlier to this antenna than to the last antenna. I'm not going to use delays in the demonstration because there are usually people speak about two beamforming regimes. One is called the narrowband regime, and the narrowband regime means that the bandwidth which you are processing is much smaller than your antenna separation. The bandwidth, of course, needs to be understood in terms of wavelength rather than frequency. So, for example, in this example, we are using 1 megahertz of bandwidth, and 1 megahertz of bandwidth, if I'm not mistaken, is 300 meters of wavelength. So provided the maximum separation between the antennas is much smaller than 300 meters, we can use this narrowband approximation. If not, we need to use the wideband approximation. So what is this narrowband approximation? The narrowband approximation basically says that if you are observing at a single frequency, then a time delay is the same as a phase change. So you can do a phase rotation multiplying by a complex exponential rather than doing a proper time delay, which is always more difficult to compute. And if you are not observing at a single frequency, but the narrow enough frequency range, then you would need to do, technically speaking, a different phase correction for each frequency to implement a true time delay. But the phase correction that you need to apply over your bandwidth is not so different. So you can apply a constant phase correction, which is valid for all frequencies. That's what happens in the narrowband regime, and that's what I'm going to demonstrate in the example. In most practical applications having to do with radio astronomy, you are in the wideband regime because radio astronomy uses very large bandwidths, so hundreds of megahertz, even a few gigahertz, and the antennas are separated by hundreds of meters, if not more than kilometers. But then if you understand the narrowband regime, you can channelize and treat each of the narrowband frequency channels separately and do the narrowband approximation in each channel, and that's how it's usually done in practice. So anyhow, just so that we know the limitations of the example I'm doing. What else we want to know? We want to know how much is this time t. And in particular, there is this angle theta, which is the angle of the incoming radio frequency wave. And it's easy to do some geometry to see that if the distance between the antennas is some number, let's call it d for distance, then this distance t, I'm using interchangeably time and distance. So this distance t is equal to d multiplied by the sine of theta. That's just basic trigonometry, and we can check with some corner cases. So for example, when theta is 0, that means the radio frequency is coming directly from above, so it's hitting all the antennas at the same time, And in that case, t would be 0. So the sine of theta is 0, but that works. And the other corner example is when the incoming radio frequency wave is coming from one side. So in that case, t is equal to d, because first it arrives here, then it needs to cover the distance d to arrive to the second antenna, and so on. So in that case, t equals d, and what happens when theta equals 90 degrees, so 90 degrees is the angle here, the sine of theta is 1, and then d times sine of theta is equal to d. So that's the formula. Now let's go into GNU Radio. What I have on GNU Radio is one signal like before. So this is an astronomical signal, but then I have a second signal, and the second signal has slightly different frequency parameters and SNR parameters, so that we can tell them apart. And the reason I'm having two signals here is because I'm going to simulate that they come from sources in different parts of the sky, and we will see how we can point our beamforming array to one of the signals, and we will not be able to see the other signal, and vice versa. So with these two entries, we can control the signal angle in degrees, so signal 1 angle and signal 2 angles. These are the angles in comparison or with respect to the vertical, so they are the angles theta of the signal 1 and signal 2. That's what happens. And then what do I have? The thing I need to do is to do a phase delay for each of the antennas. So I'm going to put 6 antennas, and the reason I'm starting with this flow graph is that it's somewhat cumbersome to put all of these together. Of course, it's a copy and paste, but then you need to tweak the parameters. So we have 6 antennas: antenna 1, antenna 2, antenna 3, 4, 5, and 6. And all of them are very similar. What we have is the astronomical signal, and we need to apply a phase shift. This is the first antenna. So the first antenna is going to be this one in the diagram, which is kind of the reference antenna, and we will not apply any phase shift. Then we will apply a phase shift of this to this antenna, a phase shift, and the phase shift here will be equal to t, or corresponding to t. The phase shift here will be corresponding to 2t. And the phase shift here will be corresponding to 3t, and so on and so forth, because we have 6 antennas rather than 4 as in the diagram. So for the first antenna, the phase shift is really 0, but let me try to show where this 0 comes from. So the thing I have here is the antenna separation times the sine of the angle of the signal. And this antenna separation, let me show the variable, is antenna separation, and it is in wavelength units. So you could have it in meters, you could have it in any units of distance you want. By using meters, the calculations come easier. We do not need to invoke the speed of light or the frequency we're observing at. But of course, that's used when computing how many wavelengths the antennas are separated. To give you some intuition, if we are observing at 1.4 gigahertz, which is L-band, that's the 21 centimeter line. So the wavelength is 21 centimeters, and then 100 wavelengths is 21 meters. So for that frequency, this would correspond to 21 meter separation between each pair of antennas, and that might be reasonable. If we go to a higher frequency, then the wavelength would decrease. So for example, at 10 gigahertz, the wavelength is 3 centimeters. So then 100 wavelengths would be 3 meters. And it's not usual that the antennas are 3 meters apart. Usually they would be further away. So for 10 gigahertz, we would have more wavelengths here. So this is where the observing frequency enters the picture. So here, antenna separation times the sine of the signal angle theta is the variable t on the diagram in wavelengths. And since that's in wavelengths, then I can just multiply by 2 pi, and that will give me the phase shift in radians that I need to apply to the signal. So that's the advantage of using antenna separation in wavelengths. And then because this is the first antenna, I'm multiplying by 0. So regardless of what I have here, this will have a 0 because there's no additional delay. Antenna number 2 has an additional delay of 1. Antenna number 3 has an additional delay of 2. Antenna number 4 has an additional delay of 3, and so on and so forth. So that's once again coming to the picture because antenna number 1, no additional delay. Antenna number 2, there is the delay t. Antenna number 3, there is this t, and this is another t. And this is 3t, 1, 2, and 3, and so on. So that's how I have set this up. And that's for the astronomical signal 1. For the astronomical signal 2, the same thing, but using the signal angle 2 in here. And the two signals arrive to the receiver, and they are also combined with the noise in the receiver electronics. And once again, we need to use different noise for each of the antennas, right? So everything up to the addition block represents the physical world. It is a simulation of two astronomical sources, the signal traveling, arriving to the antennas, and the electronics of the receiver. Anything happening after the add block is what we do also in real life to our signal using digital signal processing to beamform. And basically, I want to undo these shifts because, as we saw in the previous demo, once we correct for everything which happened on the propagation channel, we can add the signals together. But what I have chosen here is, since a priori we might not know the angles of the signals, or we might, but anyhow, we will be able to adjust the pointing angles for the beamformer, and we will see what this is. This is basically the angles which are used in these two. And the reason I'm doing 2 here is because I'm simulating 2 beamformer channels. But we could have many beamformer channels. So one of the advantages of doing beamforming digitally is that if we use more computers or more computing power, we can do more operations. So we are not limited to one single beamformer. We can do as many beamformers as we have computing power for them, because it's just a matter of replicating the digital samples we have measured and then doing the same operations, but with a different beamforming direction. So here I'm demonstrating just 2 beamformers and 2 signal sources, but we could add more. So each of them has its own beamforming angle, and the only difference between these beamforming shifts and the physical shifts in the propagation path is the sign. Since I want to correct for it, I need the minus sign. And I have -0 here, -1 there, -2, etc., etc. And you see how this goes. So it's apparent that if I set a signal angle equal to beamforming angle, then these phase shifts aren't doing what the phase shifts here do. So in the end, here I have the same astronomical signal for all of the antennas, and when I add all of them together, we get this constructive beamforming. So that's the goal. But what I want to show more importantly is what happens when we do not point the beamformer exactly at the signal. So let's take a quick look at the whole flow graph to show that there's nothing else. We have the phase shifts for the beamformer. We are adding all the signals for beamformer number 1. We are adding all the signals for beamformer number 2. So that's beamformer number 2. And then we are plotting the spectrum of beamformer 1 and beamformer 2. And that's the whole flow graph. So if I run this at the moment, all the angles are equal to 0. So that means the beamformers are both pointing to the signals. The output is the same. You can see the blue line is below the red line, and the outputs are exactly the same because the outputs only depend on beamforming angles, and now they are the same. And the signal angles are also 0 degrees, so that corresponds to both signals are overhead the array, and we are pointing the beamformer also overhead. Now what I want to show is what happens if I start moving this by 0.1 degrees, 0.02, and maybe I'm going to do 0.1 degrees. Yeah, that's more like it. So if I just move the signal, this is signal 2 and has disappeared by 0.1 degrees, then it basically disappears. I can try half, and then we see that there is some loss. So this is if I'm correctly pointed at the signal. If I'm 0.05 degrees away from the signal, then I already see some decrease in amplitude, and I can try 0.07, 0.09, and so on. And maybe it's also instructive to go beyond. So this is called a side lobe. So if I go beyond the location of the first null in the beamforming pattern, I see that the signal comes back up again, and I can do 0.12, so 0.15 comes back up again, and then 0.17 still up, 19, oh, sorry, that was too much. What am I doing here? 19, 12. If I continue, then this decreases, and I'm not going to do this for all the possible angles, but you can, if you do this, you can see that the signal comes on and off, and as you keep going away from 0 degrees, the signal is even weaker, or is supposed to be weaker. With 6 antennas, we get rather strong side lobes. So that's the reason that even at 0.5 degrees, the signal comes back up at, I don't know, some strength. Something rather important about the beamformer, which is the width of the angular width of the beam. We have seen that at 0.1 degrees is the first moment when the signal disappears. And the basic calculation is the beam width of a beamformer, or actually of a solid dish, is the same formula more or less, is 1 divided by the maximum distance between the antennas. So here is the antenna separation multiplied by 5, because we have 6 antennas. So the maximum separation is 5 times the, so 1 divided by 5 times 100. And this is the beam width in radians. So if we want this in degrees, we can do radians to degrees. And we see that it comes pretty close to the 0.1 degrees we have seen. There are some more complicated formulas which look like this one, but have some correction factors. So you might be able to see those in the literature. But the basic formula to give you a good order of magnitude approximation is just 1 divided by the maximum antenna separation, or by the dish size if it's just a single dish, the dish diameter, of course, and then that's radians, so you can convert radians to degrees. So at this moment, the signal 2 is hiding here in the noise floor because it's at a different direction from our beamforming pointing. But what we can do is to point the beamformer. So we are going to be moving beamformer 2 towards the location of the signal. And we see that now beamformer 2 is the red one. So what happens when we increase this value is the red is going to increase here in signal 2, is going to decrease there. This is signal 1. And if I continue increasing, what happens is when I match the location of the signal, then this is a situation where we have 2 different sources in 2 different parts of the sky. You can pretend these are locations on the sky. And we have 2 digital beamformers. Each of them is pointed to one of the 2 sources. And this is also a way to separate the signals. So in this example, they are nicely separated because they occupy different frequencies. But we might do something like make them 400. This is not the value I wanted to touch, but rather this one. So 400, this is neither the value I wanted to touch, but rather the bandwidth, so 400. So now they overlap, but taking advantage that they are in different parts of the sky, and that we have a beamformer and we are pointing the beamformer to each of the signals, we see that the signals are well separated in the output of the beamformer. So that's a way to look at individual sources on the sky and to take advantage that when we beamform, the beam width that we obtain by beamforming is very narrow. And I hope it's clear by the example here, but that moving the beamforming angles amounts just to changing some complex numbers here in the digital calculations that we are doing. So there is nothing that is being physically moved in the telescope. This is just something about the calculations. So we can change the beamforming locations or angles very quickly. We can scan the sky very quickly if we want. We can track objects which move quickly. We are limited by something which is called the primary beam width of the telescope. The primary beam width is the beam width of each individual antenna, which is much larger than the synthetic beam width that we obtain with beamforming. But even so, it's some beam width. So that means we cannot look at all the sky at the same time. We can only look at the part of the sky that each individual antenna can receive. But within that area, it might be a few degrees in the case of relatively small antennas, such as the ATA. We can point each of our digital beamformers anywhere in the primary beam we want. And this is very useful for SETI for several reasons. One is because in SETI searches, we are concerned with filtering out interference, because many types of interference are similar to the technosignatures that we intend to detect. So one way of trying to tell what is an interference and what is a signal coming from the star we are pointing at is to do an on-off scan. And in an on-off scan, we point first to the science target, the star we are intending to observe, and that's called the on location. and then we point to a different part in the sky, which is close enough, but still further away, so that it is outside the beam. And the hope is, if we have some signal which is really coming from the star, then it will only be present in the on scan and not in the off scan, because in the off scan the telescope is no longer pointing to the star. If we have some interference, then chances are it is something local, which is entering the telescope through one of these secondary lobes in the antenna radiation pattern, and the signal will be present both in the on and in the off scan. So we search for signals which are present only in the on scan, but not in the off scan. This has the disadvantage that we need to do 2 observations for each source. We need to do the on scan, we need to do the off scan, and that limits the amount of sources we can observe in a certain time, because we need to do the on and off sequentially. With this beamformer, there are some people which are doing the on and off scan at the same time. What they do is, one of the beamformers is pointed to the on location, to the star of interest. The other beamformer is pointed at a different location, away from the star, in the primary beam width, and hopefully any interference will appear in both beamformers, but any signal coming from the star will appear only in one of the beamformers. So that's a way of conducting on and off scans at the same time. The second interesting thing is the so-called commensal observation. So that means there is some other science going on. For example, at the VLA in New Mexico, they scan the sky to make radio frequency maps of the sky. And if you have this beamformer, one or multiple beamformers, and you can point them freely within the primary beam, then you can look at sources which are close to the main source that is being observed by the other activity, but they might be different from the main source. So in that way, you basically reuse telescope resources, you reuse telescope time, and at the same time that some other science activity is going on, you do SETI by pointing your beamformer. This is just digital processing. So yes, you need to do computing hardware to do this beamforming, but you do not need additional antennas or additional electronics, just the CPUs, GPUs, or whatever. And I'm mentioning the VLA as an example because currently a project which is called Cosmic is starting to work at the VLA. It's a beamformer for SETI at the VLA using this concept of commensal observations. What else should I comment? Maybe sometimes for questions. So any questions or comments at this point? Okay, next thing I want to comment is what is the relation between this and interferometry? So something we might be interested is in making a picture of the sky, an image of the sky, which shows the location of each of the signals we are receiving. And in a certain way, I was doing a crude picture of the sky by changing these beamforming angles before. So I did 0, 0.02, 04. And if I take measurements at all of these locations, then I kind of have a map of the power distribution versus angle on the sky, or versus location. Here we have only one angle because our beamformer is a line array, but in general, when we have the antennas not on the same line, we have two angles to point, right? So you can point in right ascension and declination, and you can make a map of the sky. Of course, doing that is very cumbersome because it either requires you to iterate through all of these beamforming locations to cover all the area of the sky you are interested in. And here it's just a line. So I have n entries, but if I want to do a two-dimensional map, I have n squared, and that is really large. So there must be a better way. Another alternative is to have one separate beamformer for each different location of the sky. So you can have a grid on the sky, and for each point on the grid, you would have a beamformer, but then the same problem, it's n squared beamformers, and all of them should be doing computations in real time. So you need a lot of computations, a lot of CPU resources. There must be a better way. And what is the better way? So if we come back here and look at this thing, maybe it looks familiar. So there is 0 times 2 pi, blah, 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 something. Now 1 times 2 pi, blah, 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 something. 2 times 2 pi, blah, 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 something. And the something is the same in all cases. So the expression I have here is basically an index multiplied by a something. And the variable I'm interested in is this beamforming angle, because I want to sweep the beamforming angle across the sky. So there's some technical detail here, which is there is the sine function, and the sine function is bothering us. But we need not worry so much, because we are only using small angles. As we saw before, we were using 0.1 degrees or something like that. So for a small angle, the sine of the angle is the same as the angle. So we can remove this sine function. And if I remove the sine function, I have the beamforming angle multiplied by something times an index. There is a 2 pi here, and so on and so forth. So what I'm trying to reason here is that the thing I have here with the angle as a variable looks pretty much like a Fourier transform, because then I'm adding everything together. So this beamforming operation, if I want to do it at the same time for all the beamforming angles, I can do it as a Fourier transform. And in this case, it's a simple Fourier transform, because all the antennas are equally separated and distributed on a one-dimensional line. So that's the reason that when I replace the sine of theta by just theta, I get a true Fourier transform. And I could do my Fourier transform, and that's efficient. And on the output, obtain the beamforming for each of the beamforming locations at the same time, and without needing a separate beamformer for each of the locations. So that's what happens with this kind of array. With a more complex array in which antennas are scattered in random locations, it's also the Fourier transform, but it's a two-dimensional Fourier transform, and it's a non-uniform Fourier transform, in the sense that in here the numbers we had were 0, 1, 2, and 3, the indices, because the antenna separations were uniform. But if we have non-uniform antenna separations, we have non-uniform numbers, but the math works more or less the same way, and we still have a Fourier transform. So without entering into too much details, in the end, the way to do this properly is, instead of trying to do this beamforming, we do this correlation. So for each pair of antennas, we compute these correlations. And then we can apply the Fourier transform to the output of those correlations, the 2D Fourier transform. And in that way, we get a map of the sky. That's the way of basically achieving beamforming at the same time in multiple directions. And we could spend more time talking about the math, doing it on paper, and there's probably some point to it, but I'm not going to do it today. The point I want to get across is doing these correlations and then doing the FFT, which is what is done in interferometry to do an interferometric image, is in a sense mathematically equivalent to doing many beamformers on a grid of points on the sky. It's just much more efficient to compute. And then finally, there is subtle detail, or maybe not so subtle, which is we already saw that this kind of beamformer, if I set here 0.1, my signals are now at 0, then they disappear. But if I set 0.2, then the signals reappear. So there are side lobes. And depending on the configuration of the array we have, we will have a different pattern in the side lobes. And the side lobes are, of course, undesired when we are trying to do an image, because these two sources, which are really at 0 degrees in the sky, and I would like them to appear just at the center of my image, at the location represented by 0 degrees, and nowhere else. But since I have side lobes, unless I do something, I will also get some image of these sources at 0.2 degrees offset, at 0.4 degrees offset. They would also appear even stronger since they are at the side lobe, and so on and so forth. So I would get this pattern, which has to do with the shape or configuration of the array. And that's called the dirty beam, because well, it's called dirty because it has all of these nuisance side lobes. And there is some clean procedure when you do imaging, and it's used to starting from the dirty image to produce a clean image by removing those side lobes. And the idea is more or less simple, is there is still the main component at 0. So if we have something which is stronger at 0 and then has side lobes in the rest of the image, we can subtract the pattern of the side lobes. So we can measure the amplitude at 0 and then subtract the amplitude of the side lobes. And then that might reveal other weaker sources in the image, and we keep iterating. So that's how most of these clean algorithms work. And that's basically the world of radio frequency with multiple antennas. You can do beamforming, you can do interferometry, and with those you can not only increase the signal to noise ratio of your signals by combining the aperture area of all the telescopes, but you can also achieve narrow beam widths and make images by relying on interferometry, which in the end is relying on the fact that for some phase shift combinations, some directions on the sky cancel out and some other directions do not cancel out. So we can electronically point, or better said, digitally point in the CPU or beams wherever we want on the sky. And this is pretty much all I had for today. So any questions or comments?